So let's do the free response question for the 1993 mechanics test. And so you started off, you're given a spring, and you have two masses, mass C and D, and they give you the masses there. And you pull this spring back 0.5 meters, and then you release it. You're given, see, what else do you know? Oh, you know that the coefficient of friction is 0.4 right there. So, and that's what this whole paragraph talks about. Oh, they let you use G is equal to 10 meters per second squared. So basically we're doing all this on a slightly more massive planet. And then determine the energy, the elastic energy stored in the compressed spring. So let's do that. So for part, you know what? Maybe I'll just try to do it on this paper. I don't know. No, I'm not going to because then I'm restricted to it. So let's zoom in. And so part A here, you wanted to know, okay, you take a spring and you compress it. So it's just energy stored in a compressed spring. So I'll just call that U sub E is equal to, and this you just have to know the equation for a compressed spring. The energy stored in a compressed spring. Oh, I'm sorry. Why is it not focused? I have to hit autofocus. All right. So it's 1/2 kx squared. Now, you guys have done this. You have the solution guide. I don't actually have one. So I don't want to do any calculator work. So you tell me what the answers are. So 1/2 of 4,000. Now, I would take the time to really look at, see, 0.5. Oh, thank you. Meters squared. So what do you get when you calculate all that? What's that?
50 joules.
50 joules. Now, hey, that's pretty easy. It's a pretty easy one. Okay, so don't, you know, hopefully you got that. Now, for part B, it says here that, well, we have block C is then released and accelerates to the right towards block D. The surface is rough, and we have a coefficient of friction of 0.4. The two blocks collide instantaneously, stick together, and move to the right. Remember, the spring is not attached to block C. Determine each of the following. The speed of block C just before the collision, and the speed of C and D just after the collision, and the horizontal distance the blocks move before coming to rest. Okay, my approach is always to try to use energy if I can, because energy is usually the easiest way to do it. There's more than one way to do these problems quite often, but and as it moves, as the spring here moves, pushes this block to the right, we're losing mechanical energy from our system because there's friction between this block. And so I'm going to start off with what I think is one of the coolest equations. We talked about this the other day. The work done by a non-conservative force results in a change in mechanical energy. Right? I don't know, probably most of you didn't start off that way, but I want you to see, even if you got it right, you probably started a little differently. And that's cool. You can do that. But so what work is done by a non-conservative force? Well, let's draw the block. Of course, we've got its weight, and we've got a normal force, and then we have a friction force, and then, of course, we have the force of the spring that's doing work on it. Now, the normal force and the weight, they don't do any work on this guy, but now the force of the spring, that's a conservative force, right? The force of a spring is a conservative force. So it's the friction that's a non-conservative force. And it's going to end up taking that energy away. So what is the work done by the non-conservative force is equal to the work done by friction. Well, what is the work done by friction? Well, it's F dot, delta S, if you want to get real picky about it. So the work done by friction, well, the force of friction is mu times the normal force. And so I'll just put mu mg. Now delta S is the 0.5 meters. So I'll just call that delta X. But here's the deal. This is a dot product, and notice that the force of friction is to the left, but the displacement is to the right. And so therefore, friction is doing negative work. If you want to look at it from the point of view of the dot product, this is F delta S cosine theta. Well, what is the angle between the force and the displacement? 180 degrees. So look for that, and that means we're doing negative work here. So negative, I think I'm ready to put in numbers here, which is so annoying. All right, 0.4, and the mass is 4. And G, they said just use 10. And delta X is 0.5. Okay, and so 20 times, what is it, 5? Negative 5 joules? Is that the work done by the friction? 0.4 times, well, let's see. 0.5 of 4 is 2. 2 is 20. And what's 0.4 times 20? It's 8. Negative 8 joules. Now that's the work done by friction. So that means my change in mechanical energy here, that's equal to my change in mechanical energy, which is equal to E final minus E initial. Well, we know what E initial was. It was the energy stored in here before I released it. When it goes all the way out here, when it collides with D, where did what kind of mechanical energy is left? It's kinetic energy. So, and I'm going to lose, but I'm going to lose some energy. So this is going to be negative 8 joules will be equal to E final, which is 1/2 mv squared, minus, and we have E initial here, which was 50 joules. And so 1/2 mv squared is going to be equal to, we'll add 50 to both sides and you get 42 joules. And so now we just do the arithmetic. V is equal to 2 times 42 joules divided by the mass, which is 4 kilograms. And then you have to take the square root. And what do you get when you do all that? Let's see. What do you get?
Oh, I get a number.
You get a number. That's right. Very good. All right. And then is it, well, I would like you guys to check my work as we go. Yeah, and actually I'm looking at the solution guide, and they did things slightly differently than I did, but it's 4.58 meters per second. Okay. All right. Now I do things slightly different than the solution guide. You know, go for it. And the solution guide is good. But one reason I really wanted to work this problem, even though this problem compared to a lot of the others is pretty straightforward. I mean, if you go through the solution guide, most of you will go, oh yeah, okay. But I really wanted to show it because I love this equation right here. The work done by non-conservative forces result in a change in mechanical energy. It's just everything. For doing energy problems, everything's there. Whether it's got friction or not, or applied forces or not. Okay. Now part C is, well, what does it say? It wants the final speed of blocks C and D after the collision, and they stick together. So this is just a super simple collision problem. So I hope you recognize that you just write P initial equals P final. Well, where was all the momentum before? Well, it was the mass of C times the velocity of C, initial, which is this one over here. And that's going to be equal to the mass of C plus the mass of D times their final velocity, which is what we're looking for. So the final velocity is going to be equal to, I can plug in the numbers now. This is 4 kilograms, and it was moving at 4.58 meters per second. By the way, if you made a mistake in part B and you use this velocity down in here, you give yourself full credit.
Oh, really?
Yeah, I mean, if you did this part right, they're going to give you credit. They really are trying to be fair to you guys when they grade this, and they don't want previous mistakes to carry on. One of the things you could do is, like, if you get stuck in part B, make up a number. Say, I'm stuck, but I know it's going to be something like 5 meters per second, and that's what I'm going to use. And then you do that in part C, you've got the points. Remember, your goal is not to get 100%, because that's impossible. You want to maximize points. So, and then you're going to divide this by 4 kilograms plus 2 kilograms. Take the time to show what it is you're calculating, please. Give them what they need. Give the graders what they need. And so you should get, well, that's was about 3 or something like that. What do you get? 3.05? Okay. And meters per second. It's still on the screen here. Okay. And then what's the other one? Part D. The horizontal distance, the blocks move before coming to rest. You can do this 2 different ways. I did everything else with energy. I'll go ahead and use force to do it on the kinematic equations, but you don't have to. If I was just up to me, I'd probably use energy to do it, but I've already shown energy, so it'd be a good review to do force. So part D, well, here are my 2 blocks together. I'm just going to draw them kind of like this. And they have a total mass of 6 kilograms. Here you've got mg. Here you've got a normal force. Here you've got a force of friction. You've got an initial velocity of 3.05 meters per second. You know it's going to slide to a stop. So here's my object stopped. And so v equals 0 here. And we want to know what is delta x. And we know that mu equals 0.4. Now, okay, for the purposes of this, I'm rewriting all this. It's probably a good idea to draw the free body diagram. Yes? Okay, thank you. All right, so look, here's your net force. So you sum the forces in the x direction. That's going to be equal to ma in the x direction. And why do you need to know a? If you're going to use kinematics to solve it, you need to know what the acceleration is. So let's add up the forces. It's 0.4 mu times the normal force. It's just 0.4 times. Now the total mass here is 6 kilograms, mu mg. And they said, hey, just use 10. I'll use newtons per kilogram just because I feel like it. So that's mu mg is equal to ma, 6 kilograms times a. Of course, the 6 kilograms are going to cancel. 0.4 times 10 is 4. So the acceleration is, and it's in the negative direction. So this is really negative 4 meters per second squared. And so now we want to know what is delta x. Well, we know the velocities and we know the acceleration. We don't know time, and we're not trying to find time. So I'll probably use the kinematic equation that doesn't have time in it, which is the 4th one, where you have v squared equals v naught squared plus 2a delta x. If I solve that for delta x, I got everything I need here. You've got v squared minus v naught squared over 2a. And so plug in your numbers now. Well, this is 0. This is negative 4 meters per second, quantity squared. The negative is outside the parentheses there. That's important. And then you have 2 times negative 4. Oh, wait, did I do something wrong? Velocity is 3.05. Yeah. and 4 meters per second squared. And this is nice because the negatives cancel. You get a positive displacement. And you plug the numbers in there. You get 9 divided by 2 is 4.5. So it's a little, what is it, a little over 1 meter or something? 1.16 meters. Okay, so let me zoom all the way out so we can see the whole problem here. And notice, hey, they like problems where you have a wide variety of topics in a single problem. So that's what you're going to get. You need to know, you need to be able to see the big picture and apply it. This you could have solved, by the way, the same exact way we did part B. Okay, except what's different is that the final energy is 0, and then this is the force of friction times delta x, and so on. So, and I think they did that for you in the solution guide. So look that over, and so, well, actually, looking at the solution guide, here's the solution guide they give you. Delta, you know, this is fine, but notice that if you just start off with work done by a non-conservative force equals delta E, it's the same thing. You're going to get the same result, but this is the most general principle. And this equation really gives you a good place to start when you're dealing with energy problems, you know, if you understand it. So it's sweet. All right, that's it for that problem.